solution series on our physics practical undergraduate physics practicals. Okay, so far about 4 to 5 videos has been done. You can check them on the physics practical playlists for first semester, depending on the semester that you are doing that very practical. Okay, within the Nigerian university or outside the country, depending on what you actually need. All right. Physics practical solutions has been done, and I'm working directly with the solution materials produced by the Young Modular Solution. So um, we'll be going straight away to look at practical on the H4. Okay, on the H4. Please, if you have not subscribed to my YouTube channel, please do that. Hit the subscription button and ensure to also forward this video link to your friends, your classmates, your departments, your junior colleague, or whoever that may need this video as regard these very particular experiments. All right, so straight away we go into the experiment for today, and I'll be explaining the solution material on the experiment H4, like I said. Okay, I think before I come here, I want to let's go back to the experiment itself so that we know what we're actually going to do. Don't forget, this is the manual that they are using for this session. Okay, 2023-2024 session, academic session. All right, so I think we are here. All right, so let me check if I have that. Okay, so this is experiment H4. I'll be going to my cam scanner where I have all the solution scanned. Okay, but I'm just trying to show you this. Okay, this is I'm sorry, let me bring my camera down. Okay, this is a H4. That's a Newton law of cooling. Newton law of cooling. So you can see the setup there, and then all the apparatus that are required are also set there. Okay, we'll go to the manual. Then let me just show the full layouts of the manual. After which we'll now move to get the theoretical background of this very concept before we go into the explanation of the practical. Please, I want us to pay attention and to be patient because this experiment is two in one. You expect to plot two graphs, somehow rough, especially in the second graph, and then there are so many calculations you are going to do at the end of the day. So the title here is Newton law of cooling, and then the aim is to verify Newton law of cooling, and by the time we go down, we'll be able to know what Newton law of cooling holds or what it's actually talking about. So the apparatus here, as we can see here, we have calorimeter, we have beaker, we have stop clock for your timing, we have the water, of course, we have burner, a thermometer, ranging from 0 to 100 degrees Celsius. Okay, then you can see the setup here, very easy to work on. Then they also have equation that we need, okay, theoretical background. Now I want us to yeah, you can read through this, but a bit advanced into the theoretical background. So we'll go a bit advanced. Let me see. No, sorry, this for M. This for M. Okay, like I said, we'll go into we'll use our let's go to the cam scanner. Okay, I think before we do that, let's look at the background study. Let's look at the background study proper. I think that would be better. Let's look at the background study of this very topic before we look at the reason. So you can still pass forward the video, you can still move the video if you actually understand the background study. Okay, but it will make sense if you follow up the background study of this very topic. Okay, thank God I'm already here. Now I've shared this link in case you want to read more about this page, science facts. I've shared a link in the description section of the video in the YouTube channel, so you can check that to take you to this very page. Okay, but the site's name is sciencefact.net, so you can check more. It is very important we understand this because um, you know many students are not familiar with heat experiment, and that's why I actually want us to understand this. Now we've been doing heating and cooling, whereby you hit a particular object and you allow it to cool for time, and then you take your time in. Maybe the object was in, maybe let's use water. Water heats up to 100 degrees Celsius, but at the end of the day you allow it to cool, and then they will ask you to take the time in up to when the water cools down to, or the temperature drops down to, let's say 40 or 30 degrees Celsius, and then they'll ask you what is the timing. That is how long did it take the object to cool from that 100 degrees Celsius to, sorry, that water to cool from that 100 degrees Celsius to 30 degrees Celsius. So there are cases like that. And we also have another one where you can do heating, where you heat the object or the very body, let's say water, okay, and then they ask you how long did it take to heat this object. Maybe you have object A, object B, maybe water and kerosene or other liquid, and then you compare their time and the rest of them. It is very understandable in that area, but when we come to this very section, well, I wouldn't use the word board. It's the same thing, but the name here is what makes it different than the title here, which is Newton law of cooling. Okay, Newton, Isaac Newton, as we all know, notice that when there is a temperature difference between two objects, for example, you bring out a chilled water from your fridge and you just drop it on the table, and you know that the temperature of that chilled water and then that environment is not the same. So when there's a temperature difference between two objects, there tends to be what exchange of heats. Okay, either the body will cool or the body become hot, because heat is only transferred when there's a difference in what temperature in that very environment. So that's what Newton law is all about. So Newton law of cooling is an empirical law to model the temperature of an object based on radiative cooling. It states that the object temperature changes at a rate proportional to the temperature difference between the object and its surrounding. This law is a reasonably accurate approximation towards some extent. Now, the law is named after British mathematician Isaac Newton, who published it in 1701. Newton did not initially state his law in its current form. It was because of the confusion arising from the concept of heat and temperature, which did not exist during this time. So you can see that the concept of heat and temperature, there have been so many contradictions as regards to that. Okay. All right, so mathematical formula of law. Now, this is the law that is the formula that is being given. Rate of temperature cooling, heat, rate of temperature loss or something. The TDT, the way the capital T there is temperature and the T here is time, and then equals to minus K into T minus T naught. They say where K is a positive constant known as the cooling constant, and then the negative sign implies that the object temperature is decreasing with time. So and then T naught is temperature of the surrounding. Then therefore an object cooling rate depends on the following. Number one, the temperature difference between it and its surrounding. Number two, the cooling constant. All right, very, very important. Now, from the above equation, we can make the following conclusion. If the object is much hotter than its surrounding, then T minus T naught is large and has a high cooling rate. The object cools rapidly. You know what that means? T minus T naught is large. Okay. Now, if the object is slightly hotter than its surrounding, remember T is the object's temperature, and then T naught is the environment temperature. So you can do the mathematics there on your own. So this is the Newton law of cooling. This is the how the graph will look like, and this is the equation 2. Okay, the rate of cooling of an object proportional to the temperature difference between it and its surrounding. So you can see the formula there, and you are going to be plotting the first graph, which is a graph of temperature against time, after which you plot another graph again, as we are going to see in the explanation section. Okay, Newton law of cooling formula. So you can see the derivation is not important, but it's good you have idea. Like I said, you can visit the website sciencefacts.net, okay, to check more about this. Now let's look at the limitation of this very law. Newton's law of cooling is limited to the following conditions. The temperature difference between the object and its surrounding must be low. Okay, now only heat lost by radiation is what considered. Don't forget we have three cases of three methods of heat transfer. We have conduction, radiation, and convection. Now, in this case, only radiation is considered. So you must take note of that while you are doing the experiment, because you are going to be you are expected to take precaution, or to write a precaution that you too are performing the experiment. Is that okay? So then we also have the next one: the temperature of the surrounding must remain constant during the cooling process. Of course, we know that is not possible. So these are the limitations that it must have. But you know that because of that, it is not possible for us to have such case. Okay, so you have seen the few things I've shown you there. I see another screenshot which I want us to see check just for further for more understanding or so. Let me see some screenshot I did. Okay, meeting law of cooling. Okay, so this one also explain when you bring shield something outside the fridge and then you notice that the body becomes hot, or when you bring hot something outside and then you see that it become cold. So there's an exchange of heat or temperature between these two, the object and the environment. Okay, so there's a temperature difference whenever this happens. So yeah, we can go through this. Now this is experimental verification. Okay, so this actually summarizes what you're expected to do. However, there are steps that will be given to you. All right, there are steps that will be given to you to follow up during the experiment, during the explanation. Okay, so this is just a guide on what you are supposed to do. Okay, so the first one is the background study here is that it says easy to experimentally verify Newton law of cooling. Now we can experimentally verify that the body cooling rate is proportional to the difference between the temperature of the body versus environment with a spherical calorimeter. Remember, calorimeter is another apparatus. A spherical calorimeter is a laboratory device that used to measure the quantity of heat transferred to or from the object. Let's assume that we fill the calorimeter with hot water. The calorimeter has mass m, specific capacity s, and the hot water has mass m1 and specific capacity what s1. Using the calorimeter, we measure the amount of heat energy lost as the temperature of the water and calorimeter fall from temperature T0 to temperature what T1 after a set time. As the temperature drops, the temperature is noted for every 30 seconds for a set time. Okay, we'll be able to know how many seconds time did they ask us to take for that of this very experiment. And there are things I want to show you in the course of that, because the table of value given to you may not be enough for you to take care of all the temperature you were asked to measure. Now, graphing the change of temperature versus the change in time gives us a cooling curve that we can use to calculate the rate of cooling. After calculating the rate of cooling, the cooling curve, we find that the rate of cooling is proportional to the difference between the temperature of the object and the temperature of the surrounding, verifying Newton's law of cooling. I think this actually gives us a background study of all we actually need in this experiment, and then with that in mind, we can actually move on to looking at what the solution entails, or what we expect to do in the experiment proper. So we are making this video. This is about 6:52 p.m. March. That is March 21st, 2024. All right. So please, if the video is not that clear, maybe you are viewing on a very low quality, try to increase, touch the screen as I always say, and then tap your screen, because I'm using this is a live broadcast. Okay, YouTube live. So try to hit on it and then try so they can view all the write up clearly. All right. Okay. So this is I'm going to experiment H4. This experiment H4. This experiment H4. Experiment H4. Okay. So all right. This is it. This is the equation. You can see the equation here. Yes, here they use a, instead of using K, they use beta as the cooling constants. Okay, so everything is there. Derivation, you can go through your notebook, your textbook, to read more about that. Okay, so now I'm sorry, I think this was supposed to be, let me rotate this so that we'll be able to see it very well. Maybe that was how I snapped it. Let me rotate this. Okay, so now that's what we have to measure. So measure and record. Number one, mass of the empty calorimeter, which is M1, mass of the calorimeter plus water M2, mass of liquid M3, which is M2 minus M1. Heat heat liquid to about 16 degrees Celsius. That's the step now. Now pour hot liquid into calorimeter to about 3/4, okay, 3/4 of its volume. See diagram above, okay. So you can see it there. So you are going to heat the liquid and then you pour into the calorimeter. The calorimeter is down. You pour it on top of. You pour it inside. Now number four, with the thermometer in the hot liquid as shown in the diagram, measure and record the liquid every 60 seconds until the temperature drops over 40 degrees Celsius. So you can see exactly what I explained earlier. So for every 60 seconds, you are going to you are going to you are going to for every 60 seconds you are going to measure your temperature for every 60 seconds, okay, until you get that. So but because if you look at the time given to you here, the table given to you, you have 1 2 3 4 5 6 7 8 9 10. You have about 10 columns, and from experience I've noticed that if you are doing that, the temperature from that 68 to that 40 degrees is more than the timing you have there. So instead of doing that, you can take it every 2 minutes. That 6 seconds is 1 minute. You can take it every 2 minutes or every 3 minutes. You understand? So your instructor will also guide you on what to do. But because if you want to take it every 60 seconds, which is 1 minute, it will not be enough. It will not be enough. It will not, the space will not be enough. So instead of creating more space, take it every 2 minutes. There's nothing wrong with that. So you can ask and then see final. So you record your room temperature, record the radius of the calorimeter, okay, using your micrometer screw gauge, okay, the depth of the calorimeter using your vena caliper, and then the rest of them. Then question now comes in for plot a graph of temperature T against time. Draw the tangent to the points, okay, the 65 degrees Celsius, this is up to 45 degrees Celsius. So please pay attention on that section because that's where we are going to hit properly. So then evaluate the values, the theta, the t for each value of the, that is from your second graph we are going to plot. Okay, we are going to plot second graph based on instruction given in question 2. Then tabulate your value in a table 4. Then after which you plot another graph again, which is question 5, of the theta, the t on the vertical and this on the axis. Then calculate your slope. You are going to get a straight line graph in this second case, while the first one you are going to get what? A curve. Take note of that. Then evaluate your graph, the value of d, be given that this is this. So you go back to that formula, that our rate of cooling formula to calculate that. That one is very easy. Once you know your mass and your specific capacity of that object or liquid, you can always do that. Then how will the variation in the radius of the calorimeter affect the rate of cooling if the quantity of liquid remain unchanged? So how does the radius actually occurs or affect diameter? And diameter, of course, is like the size of the very object. So how does the size of that object, of course, which is going to affect the area? So you can see how they are connected. Radius affect the diameter affect the area. Of course, radius affect the area too. Area of a circle or of a circular object, which is pi r square. Of course, as the radius increases, diameter increases, it means that we are going to have a bigger area, and bigger surface area, of course, does what? Increases what? Rate of cooling. So we are going to see that in the answer section, but it's good we follow up this properly. Then, what deduction can you make from the graph of this against this? Then state your precaution. So let's quickly move to the answer section. Let's see that. So you can actually see that up here. Okay, so I would just assume that which is MC, which is a mass of a calorimeter, is 0.028 kg after conversion, and M2 0.058. Then to get our M3 we subtract and we got this. Now room temperature, of course, 25 degrees Celsius. Raise of the calorimeter 2.5 cm. Depth, that is length of the calorimeter, is 10.5 cm. We just assume, so you use your value based on that, and then the nature of the graph become this. So that's what the young module solution gives you. Okay, nature of the graph. The graph must extend from 68 degrees Celsius to 45 degrees Celsius. take note of that. Now, looking at question 2, that's what I'm trying to explain here. Question 3 says you draw tangents to the points at theta 65 degree, this and that, deduce small tangent of this is no. Now look at the work here. Come this side. Now at 60 degrees Celsius, that's where they say you should start. Draw a line, a dot to meet the curve. Then just at that section, I wouldn't tell you how much or how big it is, just use your common sense. Just along that section, between that, above that 60 and below that 60, draw your tangent. Then find the theta, the t, that is change in temperature. As if you are finding slope. Normally, if you want to find slope of a curve, we draw a tangent to the curve, and that is where the differentiation comes from. If you know differentiation in your calculus, differentiation from first principle, you know that the derivation was done in this manner, where a curve was gotten, a graph was plotted, and the curve was gotten. Then from that curve, a tangent was drawn at the particular point, and then from that tangent, dy dx was gotten by changing y by changing x was gotten. And then we now see that the limit of that as change in x tends to 0 gives us the dy dx of that very function, of that very curve at that particular point. So that's exactly what they say you should do here. So at 60, trace it to the point, to the curve, draw your tangent, take your slope, the theta over the t. Remember, you plotted theta against t. Then at 50, do the same thing. At 40, do the same thing until you get to the last value which we were asked to take. And I said, now for clarity, this is what you are expected to do each point. Let's say at point 60 and 45. Okay, I did for point 60 and 45 for clarity, so that it will not be that rough. So I now came down here and said, I trace it. Now at that 60, I have the theta dt, and then above it, which is the theta 2, I have 62. Then below it, I have 58. Then on the time side, I have 1.5, and then I have 1. So I subtracted, I got this. So if you notice, this is going to give you a negative graph. Okay, it's going to give you a negative graph. Okay, that's why that formula gives us negative. You check the formula that was given to us in the theoretical background, you see negative there. That's how it's supposed to be. Then go to 45 degrees. Just the way you take your slope. Once you draw your tangent to that very point, the way you normally take your slope after drawing your triangle is the same way. But the only thing is that you are going to get negative on the time axis parts. Yes, on the time axis parts. Now, how do you do that? Now, check that of 45 degrees Celsius. Now, we had for 50 minus 44. Then we trace down the highest number, the 3 correspond to the 50, while the 4 correspond to the 44. You see, negative slope is a graph. When your graph is taken from the left hand side, that is a negative slope. So the number on the horizontal changes. That's what happens on negative slope. It changes. The smaller number goes to the bigger number above, and then the bigger number goes to the smaller number above. You understand what that means? If you didn't get it, well, please drop a question in the comment section or check me on my WhatsApp for more explanation. Okay, so that is how to take graph on negative on a curve like this. All right. Before we round up here, I think let me reverse this. Stop, please. Just give me some time. I think let me reverse this again. Trying to reverse this. All right. Thank you. Okay. So let me take this up now. So you do the same for 65, 55, and so on. Note, tabulate your value. Now tabulate your values on the table. So you tabulate your values on the table as you are being given. Okay. The table says theta minus theta naught, which is 35 minus 25, 60 minus 25. Okay. And then theta naught is at room temperature. Then each of those values you calculated, you tabulate them as shown below. Now we only calculated for 45 and 60 degrees for sample. So you see the value will be what? Decreasing. So you can see that the value is going to be decreasing as seen there. So when you do that, you are going to get this kind of graph. This is what you get. So you check your temperature is decreasing, and then the theta dt is also decreasing. So I think it's clear. So we are going to be plotting theta and theta, not again the theta dt. So it's a bit rough. It's a bit rough. So I will expect you to ask question. So check my channel, my WhatsApp 09157293443 for more. In case you have challenge, you can also drop a comment on the comment section. I will be there to also answer you. Okay. We'll move on to almost the last parts. Yeah, this is where we are asked to calculate our B. So what we do, we go to the equation and make B subject formula. All right. So we go to make B the subject formula. But first and foremost, we try to ensure that we make the theta over theta minus theta the subject formula, which is the slope of the graph. Our slope formula for the slope is going to be, okay, it's already written under the graph I sketch here. Change in the theta dt, again change in theta minus theta naught. So whenever you have an equation that relates a particular experiment you have done, and that equation is a straight line graph, there's possibility for you to transform that equation to look like equation of a straight line, which is y equals to mx plus c. So when you do that to that equation, our Newton law of cooling, you are going to get this, where our slope becomes b a over mc. And then of course, to look for our b, we cross multiply and then we divide through by a. All right, so our value for C is 4,200 or 4.2 times per 3. Okay, that is the specific capacity of water, and not 4.2 times per minus 2 or minus 3 that are stated in the book. So make sure you do the correction. So let's assume that our slope is 0.48 per second. That is the unit. Then we put that. So the area of the calorimeter looks like a cylinder. So the area of the cylinder, okay, becomes this pi r squared plus 2 pi rd, the total surface area of a cylinder. Okay, that is supposed to be our height, which is the depth. Okay, so they use this, so we have to use d. All right, so finally we have you substitute everything to the formula and make sure you do appropriate conversion to ensure that you have the SI units given. Kilogram for mass, then meters for radius or for distance, and then so on and so forth. So after that, you are going to get this very value. So the units there is stated kilogram per Kelvin per second square. All right, so I think that is that. Then the next section, which is the last part, talks about let me see. Sorry, let me flip this again for the last time. Okay. All right, so the other one talks about the relationship between that graph, in the graph, what we observe in the graph. Okay, as the radius increases, okay, I think that was based on the question that was asked. We were asked to check the relationship or how radius affects the rate of cooling. So like I said earlier, as the radius increases, the diameter increases. As the diameter increases, you expect the base, which is the size of the calorimeter, to increase, because normally if you want to draw a cylinder, okay, just specify the diameter or the radius, you will be able to get the base or the size of that cylinder, and of course the heights can also be given to you like that. So the area, the radius affect the area, diameter also affect the area. So as the diameter or area, the radius increases, the area increases. So when there is a larger surface area, the object tends to cool faster. For example, if you have water in a basin and water in a cup, the same quantity, like hot in being equal, the same quantity, you expect that of basin to cool faster, because that of basin offers larger surface area to the atmosphere. So they tend to be cooling than that of when you have the object or the water in the cup. All right, so question 9 talks about the relationship between what you can observe in the graph. So the graph is a linear graph. It's a linear, you have a straight line graph, okay, in the sense that as the rate of the temperature is decreasing, the temperature itself is also decreasing in that manner. So from the graph we have, the temperature drops, the other one also drops. So you have a linear graph in that case. Of course, number 10, precaution. As usual, you ensure parallax error avoided while you are taking your reading on the thermometer, and of course other metering device. Then you ensure that the temperature drops was monitored at regular time intervals. So meaning that if you are asked to take the temperature at every 1 minute or two minutes, you ensure that every 1 minute you do that. Okay. Then you also ensure that you use the right or the good lagging material. Lagging materials are those materials that ensure that there is no heat loss or gain in the environment. So you do that, and then not just that, you were asked to transfer the water, okay, to the calorimeter. So you ensure that the water was transferred quickly, okay, so that there will not be any temperature loss in the environment. Rather, we need to know the temperature gain by that very calorimeter, because if you don't do that, we'll not be able to ascertain the amount of temperature gain by that calorimeter. You can check other heat experiment, okay, that we have done, and then look at the precautions stated. Okay, the precaution in all heat experiment are almost the same thing. Okay, so you look at that. Okay, so please, if you have any question, please drop it on the comment section, and let's see how far this we can go. And don't forget to like, okay, share, and then comment, and then not just that, subscribe to the YouTube channel, and then forward this video to, of course, share this video to your friends who might also need this. Once again, this is the Young Modulus, and I'm always here to help you out. If you have any question, please don't forget to reach me out on my WhatsApp group, or drop it on the comment section. I will also be there to answer you. Thanks, and God bless you. All right, so at this point, I will see you in the next video. Our practical solution series has not ended. We are still on top of it, so we'll get there when we get there. All right.